1.41 or 1.42. It's something that we don't know.
All right. Okay.
So it's just like they do this round up. So this is then the second source of error. So if we have, like, for example, yeah, we do the best that we can. We specify this according to the values given to us. Yeah, 121 degrees C, and with this flow rate and then pressure, and then also this stream 2 with the same flow rate and pressure and so on. And then it gives us like 45 degrees C, and then what we have here is 46 degrees C. Yeah, I mean, so be it, I would say.
Right. Okay.
Right, so it's not really it's not like a big deal. So
Okay.
213 kilo. Sorry, one minute, yeah. So that means this stream number 3 is 10.49. See the total flow rate is also different already, right?
Yes.
So it's not 10.49. It's something else. So it's a fine, yeah. I mean, it's fine.
All right. Okay.
At least what's in doing the simulation, number one, we need to understand the process. Yeah, as you go along, you will get more experience, and then you can understand process faster than you can do now. And then the number two is that when we find these discrepancies, we have to be able to explain it. So if we are able to explain why we have such differences, that is not a problem. That's not an issue. Yeah? Okay. Okay, close. Yeah. So now we go to the heat exchanger 201. See, you see this stream number 4 is already calculated. Yeah, very strange. Because you specify the stream number 4, which you should not do. No, you don't connect it first.
Okay.
So you remove any information that you put in the exchanger and then the stream 4. No, don't disconnect. Just remove any information in stream 4.
Oh, in stream 4.
This is also okay. So remove all of this because this temperature, pressure, molar flow rate, and then composition, it will be calculated, yeah, accordingly.
Okay.
Okay, very good. So yeah. So now, okay, yeah. Exactly, yeah. So you have specified somewhere in the old calculation. What have you specified in the exchanger? Go to composition.
Should I delete this, or should I just delete the whole heat exchanger?
Just delete disconnect that stream 4 first. To the right a little bit. No, it has to be like a tick, and then we can just click it. Oh, okay. Oh, I didn't know that we can do that. But okay. Double click on that exchanger. Okay. Go to design, yeah. Parameters. Go to parameters. Nothing, yeah. Worksheet, nothing. Duty, nothing, right? Okay. And then stream 4. Have we specified anything? Because it seems to be like double click on that stream 4, maybe.
Nothing.
It's nothing. Properties, composition. See why it has this already, that molecular mass, right? So it's very strange because it should not have anything.
Maybe she just delete it.
Just delete that, yeah. You know what? It should not get any data, yeah.
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 Okay.
And then you connect it. See, it doesn't have anything, right? As it should be. Connected. Click, yeah, and then drag. That one. Drag, yeah, exactly.
Right.
And then yeah, we fill in the yeah,
parameters.
So, okay, now before we do so, yeah, let's think. Let's think. Yeah, you have learned. Yeah, you have learned heat transfer, right? Heat exchanger. So what is then the equation needed to calculate? I mean, yeah, it's going the equation needed to use in this exchanger. What do you
Molar
think?
flow rate, heat capacity,
Mm-hmm.
duty,
Yeah.
delta temperature difference.
Yeah, exactly. So what Shafiq writes here is Q equals to mCp delta T. Right. So we have one equation. We have four unknowns now: Q, M, Cp, and then delta T. Yeah, delta T we can split them into two variables. That means we have 1, 2, Q, M, Cp, T inlet, T outlet. So we have 5 variables. But we have only one equation. So we need to have 4 more, right? 5 minus 1. So we need to have 4. We have to have specify 4 data in 4 variables. So M, we know it M, eh? So M has been specified because we have connected stream 3 into this exchanger. So it will use the same M, yeah, the same M because it's mass balance. So M is known. Cp is also known because we know what the composition is. Right, so Cp is then calculated accordingly. So 2 of these remaining 4 variables have been specified, right? So M is there, Cp is there. Now T inlet and T outlet. Yeah. So T inlet, it has been specified. Exactly. Yeah. So what is left is the T outlet, right? So this T outlet, you can either specify T outlet or the delta T. Yeah, like what you point out here. So if we specify delta T, that means T outlet will be calculated accordingly. Or if we specify T outlet, and then delta T will be calculated accordingly. So that's the one equation for the heater. Yeah, so just put anything that you like, either the T outlet or delta T, whatever you want to input. Duty we don't know, yeah? I mean, do you know what the duty is?
Nope.
That means you you don't want to specify the duty. Unless if you know the duty.
I don't.
But normally we don't know.
They only provide the utility usage of
Utility
medium pressure steam.
usage
Yeah, 7,000 kg per hour of medium pressure steam.
for this particular heat exchanger.
Yes.
Okay. That's the steam, yeah. But okay, fine. It's something that we don't know. We even also don't know what the pressure level of the steam is. So if we don't know what the pressure level of the steam is, that means we don't know at which temperature it condenses. That means we don't know what is then the enthalpy that is going to be given to the stream. So if we don't know what the enthalpy is, and then we cannot calculate what the flow rate is. It's like but okay, so 209 is then your temperature outlet. 109.
The temperature outlet specified here is 154.
154. Okay.
Yeah. So do we fill it up here or in the worksheet?
Yeah. What I would do normally, I don't specify delta T. I just specify temperature outlet because that's what I would like to have.
Yeah.
If you specify to 154, just use 154. Okay. Now. Okay, so that QMCP delta T is done, but then it still requires us to know what is then the pressure outlet. So that is typical because it is related to the flash calculation in the heater.
Okay.
Yeah. So we need to have pressure temperature calculated. So then it will then know what is then the condition, what is then the phase of the stream. Yeah, because now if we don't specify the pressure or delta P whatnot, so we don't know what the vapor condition is, right? You can still remember that phase diagram, yeah. So we need to specify either the vapor fractions or the pressure. But in most cases, we only know. I mean, we know what the allowable pressure drop that we can have, for heat exchanger, for example, yeah, we know what the pressure drop is. So we typically specify the pressure drop, and then based on that number, based on the pressure drop and then temperature, the vapor fraction will be calculated accordingly. So that's basically what we do. So in this case, yeah, if you, this is stream number 4, you can specify the pressure drop is 0.1 bar, yeah. Okay.
0.1 bar.
Yeah, 0.1 bar. So it's a 15.4. So you can just specify pressure drop, yeah. I mean, I would prefer the pressure drop rather than the outlet pressure.
Okay.
And then you go to design parameters and then pressure drop, yeah. Yeah.
So we got the duty.
And then we have the duty, right? And then we have the duty calculated. But this isn't the duty, yeah. So if to get to this number of 7.2 tons an hour, yeah. So that means we need to divide this number, this duty, by 7.2, and then we know the kilojoule per kilogram.
Yes.
Yeah, and that kilojoule per kilogram number we have to find in this steam table. What is then the corresponding condensation temperature?
Okay.
Yeah, but for this point in time, we don't really care. Yeah, we just need to know. Okay, so go back to worksheet. So we see what is then the phase, the phase of the
liquid.
So it's still liquid. Yeah. Okay. What is then the fluid package that we use? Basis 1.
Unique.
Unique work. Yeah. Okay. Fine. No. This stream number 4, this is going to be further heated in this fluid effluent heat exchanger E2O2. Okay, and
it will be from the shell side.
Yeah. Okay. I need to stream number 4, number 5, okay, and then 6 and 7.
Yeah.
The 6 and 7 we don't know. There is a workaround because we don't know. Yeah, I mean we can specify stream number 6. In this case, we can specify stream number 6, and then we then specify the outlet temperature of stream number 5, the stream number 5 temperature, and then HYSYS will then calculate the same way like we just did. The one we can do, or yeah, one more things that makes more sense is to remove this, to delete this shell and tube heat exchanger. This is what I would do normally. So I will just delete this and then make a heater to heat this from stream 4 to stream 5. Make a heater. Yeah, give some space. 4, number 5, energy stream. No, another energy stream. 202. 202. And then delta P is so it's about 0.4 bar. 0.4 bar. 0.4. Yeah. So the duty is that duty, huh? Okay, now we have done stream number 5. We need to continue to the reactor. Yeah, we will deal with this stream number 6 and 7 later. Yeah, we will see how. Now
Reactor.
Okay. Yeah, and this is like a packed bed reactor. So we have to select the PFR type of a packed bed. That one.
This one?
Yeah. Yeah.
Okay.
Because okay, yeah. Go on. Number 5. That's number 6. Yeah. Now it says here it requires a reaction set, so we have to define the reaction. So we go to the reactions, and then that reaction set is nothing. Yeah. So we close this window. Close this window, and then we go to the left. There is this reaction setup in the. If you go to palette, and then we go to the. Go to back to the properties.
Properties.
Reactions. You can see that reactions on the left. Yeah. Here where we have to define the reactions. Click add. Now, add reaction. Yeah. Now, so now the question is then, are we going to specify this as an equilibrium, or if you have the kinetic or what is that, conversions and the rest?
So
I think since we have the kinetic, it's better to specify the kinetic. Yeah.
reaction kinetic.
Yeah. This one. Delete one.
Okay.
Okay, and then double click on that. Double click on that RXN one. Yeah. Now we go to before do you have the document with you?
Yes, I do.
Can you put it on the screen?
It's on my WhatsApp.
On your WhatsApp. Okay.
Yeah.
So I'll show you. So the kinetic is then the TCDT. Oh yeah, sorry. Yeah, we have to specify the component first. Yeah. So good. Thank you. Add component. So we have this is a methanol dehydration. Yeah. So we have to methanol. Components is methanol, and then the water, and then DME. So we have to add all of them. And then the stoichiometric coefficient. So we have methanol is then 2, but it is -2 because it is on the reactant side. Water is 1, and then the DME is 1. Enter. Balance error, you can see your balance error is 42.
Where is that?
That one.
Here.
So it has to be 0. So that means there is something wrong with either the stoichiometric coefficient or the component.
It's 2 methanol DME plus H2O.
Okay, so that 2M2C for all, is that the DME?
I think so. Hold on, let me see.
Double click on that that 2M2.
Alcohol. Oh, okay, this is wrong.
Exactly. So
It's this one, right?
Yeah, that one. And then replace.
Oh, okay. Sorry. Let's remove. replace. Okay.
Yeah. Close. And remove that to M2. Yeah.
How do I delete this?
Yeah. Okay. 1.
Okay. Balance
See.
0.
Yeah, because it calculates the this small balance.
Mm-hmm.
Okay. Yeah, and then on the basis is then if you see the document with you, we can see the minus reaction methanol equals to K0 times exponential of minus E0 RT multiplied by the partial pressure of methanol.
Mm-hmm.
Yeah, so that means the basis is not the molar concentration, but then the partial pressure of methanol. So the change the molar into partial pressure,
Methanol.
and then it's going to be in the vapor phase. Yeah, methanol. Yeah, and then basis unit is kilopascal, right? Yeah, and then the basis unit is that one is correct. So it's kilopascal, and then the rate unit. So the rate unit in here is always kilomole, not always, depend here. So kilomole per meter cubic catalyst, and then it's not per second but per hour. Yeah, that one. Okay. Now, it's moving forward. Yeah, it's a 2 methanol mix DME and water. So the forward reactions, you can see that forward reaction. So we need to have A, E, and B, and then you can see the equation help down there. You know what A, E, and B, what they are for. So A in this case is then the like a collision frequency or pre-exponential factor. So in here we see that's the 1.21 times. Okay, so 1.21 E6. Put E6, and then space. Can you put space? No, nothing. Yeah, no unit. Yeah. Okay, then and then just enter.
All right. Okay.
Okay. And then the E0 here is then the that E is then 80. This one is we have to be careful. So kilojoule per mole. Yeah, kilojoule per mole. Yeah, that one. Okay. So it's all green. So we have specified the forward reactions. So if we don't specify anything in the reverse reactions, it will consider everything is 0. Yeah. So no reverse reactions if we don't specify anything, which we don't. Yeah, it's all empty. Can you see that window?
Mm-hmm.
How do you get those values again? Oh, so it's Safik, it's on page 67 on the this appendix B, page 67. You have the I don't know if Safik has the document.
From textbook in WhatsApp group is page 1108.
Oh, okay. So it's appendix B. You go to appendix B and you will find this DMA plans, and then you will get the constants for the reactions. Yeah. Oh, very good. Any other question?
No, I'm okay.
Good. So we have specified the reactions. Yeah. Be careful. Again, be careful on the components and then the stoichiometry of the coefficients, and then make sure that the balance error is 0. And then for specifying the reactions, be careful on that reaction phase, and then the base component, the base units. So units are very important here. So please be careful. Yeah. So we close this. And then add to wait. This is still showing you that yellow. Add to FP. Yeah. Add to fluid package. Add. Yeah. Yeah. And then go back to simulation. This is no. Yeah. Why is then stream number 6 is already blue? Have you specified something in that stream number 6?
We specified the temperature when
Remove.
okay, remove.
You're killing me. Yeah? So we don't specify again, yeah. We don't specify anything for the output stream. Output stream is always calculated. Yeah, that's clear, yeah.
All right.
So now, so we have specified the inlet. Oh no, inlet is calculated. Now we are going to specify something in the block, the calculation block. Requires a reaction set. Go to reactions then. Yeah, specify. Yeah, set 1. And then unknown dimensions because it's a plug flow reactor. So, and then the K0 is also saying that it's a per meter cubic of the catalyst, right? So we need to specify the volume of the reactor where the reaction can take place. So we go to design maybe, yeah. Go to design parameters. No. Or rating maybe rating. Yeah, this one. So I think we go to this reactor. In the previous page, we can see it's a reactor is then carbon steel, and then the diameter is 0.72 meters.
Okay, R201.
201, yeah. 0.72 meters, and then the length is 10 meters. Yeah. Okay, so we know the volume, we know the size of the reactor, but then we don't know what the delta P is. In this case, yeah. If you can see, wait, go back to the rating. Go back to the rating. So it by default the void fractions is 1, so that means it's just like a hollow pipe, yeah. So in this case, we just assume it like a hollow pipe, or we typically put like void fractions of 30%, for example. That's what we typically do. But for this example, we can just leave it at 100%. So it's like a hollow pipe.
Okay.
And then the delta P. So again, this delta P is also very important. There is 1 minute, yeah. So we can either specify the delta P here, or we can just let HYSYS calculate the pressure drop, because we have specified the length and the diameter of the reactor, and also the void fractions of the reactor. So if we let HYSYS calculate the pressure drop using the Ergun equations, that's also fine. You can click it. Yeah, it's a 0 because it's a very huge reactor. Anyway, so okay, yeah, and then we can see the composition. See, so we previously don't have any dimethyl ether. Now we have 50% of the AME and 50% of water, and then almost no methanol. Right. So and then we go back to the conditions. You can see the temperature is as well. Temperature is calculated accordingly. Yeah. So you are not supposed to specify the temperature. So if we compare this to the stream table, you can see the stream table in stream number 6 is the outlet temperature is 364. And then in our case, it's 392. Okay, so that's one difference. Why is it different? We can see in the compositions as well. In our case, the methanol reacts almost completely, right?
Yeah.
Okay, from 0.98 to almost 0. But in the stream table, we can see the if you calculate that, it's the methanol only reacts for 80% roughly. So 20% of the methanol is not reacted.
All right. Okay.
Right. So
can we put like the efficiency of the reactors, or should we not?
Yeah, in this case, if we want to match this, so we could do something like that, like for example, if you want to reduce the length of the reactor, that's one item. So if you make the reactor shorten, we can see what happens. So you can put like a case study. So okay, you stop here. No. We'll make it more intelligent. So
Okay.
okay, so that's a Stone Age style. It's a correct, it's a correct. So you can just vary that manually, but I will show you how to do this automatically. So you go to case studies on the tab. Go see. Can you see case studies there? Case studies.
Okay.
Yeah, exactly. So add, yeah, exactly. Now just close this palette, yeah. I mean, it's really irritating. That close it. So now go to just go to variable manager, for example. Let's see what happens. Okay, yeah. Maybe we can do it because this one we have to search for that variable. Just close this, and then go back to that flow sheet. Yes, yeah, go back to that flow sheet, and then double click on that reactor. Where's that length again? Rating. Right click on the length. No, the number. Right click. What do you see? Because I cannot see it. So for me, it's dark. It's a blank dark.
Oh, it's select all, copy, paste, send to, print data sheet.
Send to. Is there send to case study 1?
Yes. Case study 1. All right.
As the independent variable. Yeah.
Yes. Right. Okay.
Yeah, independent variable. Yeah. That
Yes.
means this is then the variable that we are going to vary. Okay. So if this then what we are going to vary, what do we want to see? We want to see the methanol conversion. So or maybe the methanol outlet flow rate, right? So we do it. Okay, go back there. So we make it more intelligent. So worksheets and then composition. Yeah, that methanol. You can just put everything. Put those 3 if you want.
Okay.
Yeah, and then the okay, so variables is there. Go up a little bit up, and then case study setup. So we have selected the variables, yeah, and then case study setup is that okay. So the current value, so we want to vary the tube length, yeah. The current value is 10. So we want to vary it from, I don't know, maybe you want to vary it from 0.1 meter or 1 meter. I don't know, up to you.
1.1 is okay.
0.1 is okay, up to you. I mean, until start 0.1 until end, or step size. I don't know which one do you prefer.
That's that.
Until 10, and then step size is maybe, I don't know. You want to have it like 0.5 means it's going to be
Less than
no,
this.
there's no 0. Yeah, 0 does not work. You have to put some number. 0 means there's no reactor.
Yeah.
So 20 steps. Yeah, okay. Okay, and then what more? Yeah, just click run.
Okay.
Done.
Result. Yep, done. 100%.
Okay. Okay. Results. And then see, you can see. Maybe you can get the plot. Yeah. See plots. And then that variable, change it to methanol, for example. Methanol.
Yeah.
See, you can see if we shorten the reactor, the unreacted methanol gets increased, which makes sense, right?
Yep.
So and then you can see this curve here. I think when you learn reaction engineering, you can see this curve for reactants, right? It will then go lower, like an exponential term, like in this case. So we need to give it like 20% left. But if we see this curve, that means we will have a very short reactor. Okay. So so at least now you see this, yeah. What I personally have learned about this appendix B Turton is that because we know already that we have thermodynamic some errors in thermodynamics, some differences, yeah, and errors, and then that reaction kinetics number, it's also not really accurate. Means we need to if we use the current kinetic number, that K0 and an E, we will never get this 80% of conversions using reasonable length of the reactor.
Okay.
So what we did and what we could do now is then to change this how do you call it, this collision vector, the K0, in such a way, yeah, the end of the reactor we still have that 20% of methanol. Am I clear or no?
Not really.
Not very clear. Okay. So go back to that properties. Go back to properties.
So
The goal,
we
yeah, the goal.
change the KO.
Exactly. So that A, because the goal is then to we want to try to match this, yeah. The goal is then to put
Yeah, I see.
to get methanol reacting only 80%. So we have the A, so we can reduce this A so that we can get the that 20% of methanol at the end.
Okay, so by
So how
what
do we do this?
what number do I change it to?
We can do it in the Stone Age way. Case study again, yeah, you could do so, yeah. You can try.
Oh, okay. Wait, case study.
This is case study 2, right? Exactly. And then very good, yeah. So you just take methanol, I mean, because we are only interested in methanol. Very good. So you learn very quickly, yeah. Case study setup. So now we start with unit. Is there any unit there? I don't think it is.
There's no unit.
There's no unit, yeah. So you could start like I don't know.
What's the standard? I'm not sure of the standard value of a KO.
Or you can start from 0, if you don't know, or maybe 1. Or maybe start, this is 1.2 million, yeah. 1.2 million, you can start with like 1,000, for example, or 10,000. Okay, and then it ends like now, well, let's say n is then the current value, I would say. Because with the current value, the step size is
0.5.
no, it will take you eternity. 2,000 calculation. See, you can see steps is so make
Okay,
this steps is reasonable, yeah. Instead of step size, remove that step size, delete step size. And then exactly. Make, I don't know, 20, 30, 50.
Let's make it 50.
50, yeah, make it 50. Run.
Okay, this is gonna take a while.
Oh, it takes into account as well case study 1, yeah.
Really?
I see. This is that the length of the reactor is case study 1. Stop.
How do I stop?
Done, yeah. Is it complete? No, yeah.
It's
Complete, yeah.
yeah, complete. I think so.
Scroll down.
Yeah, it is complete.
Okay. Complete, and then we will need to see mole fractions of methanol. Let me check, yeah. So in this stream 6, the mole fractions of methanol is how much? 64.9 divided by 3 to 8.3. It's about 20%.
So
It's about 20%, which is 0.2. So
it's actually probably less than 1,000.
So less than 20,000 for sure. You can try to rerun this case study, and then we can start from that. You can start from 1,000, and then end is the end is 20,000, right? Yeah. And then it's 100. Which one do you want to specify, Aisha? Step size or steps?
Steps, sorry.
Remove that step size. Delete. Enter. And then steps. 25. Yeah. Mine. Is it done? No, not done.
No, not yet.
Hey, be patient. Done? Oh, not done.
It's done.
Go back to plots.
Okay.
This
is 20%, right?
Yeah, about 20%. That 2,000.
So the exponential factor is around 1,700. 1,700.
Yeah, make it 2,000. Yeah, I mean, whatever. It doesn't sound nice.
Okay.
Make it 2,000.
Okay, 2,000.
Okay. Now, yeah, make it 2,000. Enter, and then go back to that simulation. I think that case study. Yeah, this one. Go back. See, it's a 13. Yeah, okay, fine. At least we have something. Yeah. So so that's one way that we can play around. Okay, so 10:30, you can better save this case. Save this case, and then we'll see each other again next week, right? So in the meantime, so now you have the stream number 6. Yeah. Make a cooler, and then use the energy from that cooler to hit that E2O2. Yeah. See how you can do that, and then let me know next week. Okay.
All right. Okay.
Good. Thank you.
All right.
Have a nice weekend.
Yeah. You too.
See you next time. Bye-bye.
Bye.